welcome guys. So this is my new series of the set theory. So I'm planning to cover some basic, some interesting set theory results, and maybe the axiom of choice, Zone's lemma, continuum hypothesis, and the Cantor theorem, and the many countability or uncountability discussion. So before I start, please subscribe to my channel. So in this video, I want to talk about this famous Cantor theorem. Basically, this is the diagonalization argument, the generalization of the diagonalization argument. So the idea is that given a non-empty set A, and PA is a power set of A. So the idea is that we want to say that the cardinality of the power set must greater than strictly greater than the cardinality of A. Okay, so this means that if you have an infinity set, then there must be some infinity set which their cardinality is bigger than you, and that set can be your power set. So this is somehow like a beyond infinity. So you have one infinity and you have power set, so you get two infinity, you can get three infinity, four infinity. So this is somehow the controversial results of your intuition. Okay, so let's give the proof. So idea is that if the set is a finite set, then number of element of A is n, then the number of power sets 2 to the n, right? So this is like elementary school results. So we know that 2 to n strictly greater than n for n greater or equal to 1. So this is trivial result. So for the finite sets, this statement looks so trivial. Okay, but how about if your A is infinite? So this is a difficult results. Not trivially. Okay, so let's see the set theory proof. So the first we want to say that the cardinality of A must less than PA. Okay, so the idea is that if you given a set of A, right, given an element of A, then you can create a set with single element X. So it's like a singleton in its power set of A, right? So the remaining, so that means A to PA is injective. So the remaining part is to show that A is different from PA. So the remaining part is to showing that they are different, because we already showed that A is injective to PA, so A is less than PA. Then we want to show they cannot be the same. Then it will directly imply that PA will greater than A. Okay, so the idea is that there is no surjective map from A to PA. So that means they cannot be the same. Okay, so the proof is so interesting. Okay, so let's assume that we have such F and surjective, then create a set called B. B means that collect all the element of A such that X is not S do not belong to F of X. So now you see, now F of X is a set of A. It belongs to a power set. So it's reasonable to tell that whether a set of A belongs to some element of the power set of A. So notice that B belongs to PA, right? So B is also a subset of B is also an element of PA. Okay. So now since F is surjective, right? So that means if there exists A in here such that F of A equals to B. Okay. Okay, so now interesting happen. So I can ask whether A belongs to F of A, right? Because F of A is B. Okay, so let's say A belongs to F of A. So A belongs to F of A, right? That means A do not belongs to B. But B is exactly F of A, right? So these two conditions are contradictory, right? Because if A belongs to F of A, then A do not belongs to B. But B is F of A, right? So this is a contradiction. So there's a contradiction term you can put in here. And also, if A do not belong to F of A, then the A will belongs to B, right? But B is F of A. So these two statements are also contradiction. Okay, so whether A belongs to F of A or whether A do not belong to F of A, both leads to contradiction. So it tells us that the F cannot be surjective. And if F cannot be surjective, then that means A cannot be. There's no injective and a surjective map from A to PA. But we know that there is an injective map from A to PA. So that means PA is strictly greater than A. So this proves the famous Cantor's results. Okay, So there's a other discussion I want to talk about. So let's go to see it. So contradiction, right? Contradiction. So we know that if somebody give you a set A, right, then you can construct PA, right? So people like to use 2 to the A. So we know that A is less than 2 to the A, 2 to the 2 to the A, less than 2 to 2 to the A. Okay. So one interesting, one direct results. So the implication is that somebody give you the integer, which is cardinality is the same as the positive integer, and the same as Q. And I may create another video proving this idea. Okay, and you can show that this is the same as n to the n cross n, or any like the finite n. So this is the finite tuple of n. Okay, and then if you do the power set of n, and it's easy to prove that this is R. So it's less than R. But the question is that is there A such that A cardinality of A is greater than n but less than R? Okay, so we are asked about whether such A exists. And the answer is that this is a famous called the Continuum Hypothesis. So it's developed by Cantor. So it's developed by Cantor. The answer is we don't know. We don't know from axiomal choice. From the ZFC set theory. So basically, if you assume that ZFC set theory, you assume axiomal choice, then you still cannot say that A exists or not. So this can go to the famous Gödel results. The Gödel results of why actually the continuous hypothesis is like the undesirable problem in the ZFC set theory. Okay, now you can ask more powerful results, like whether R is a 2R, whether there's a other infinity force into R in its power set, and also 2 to 2R power set. So there's a generalization of the continuum hypothesis, says that the power set of A. So there's a famous conjecture. But this problem is also undesirable, such that some people conjecture that if somebody gives you a set of A, then you can create a power set. We know that it's greater, right? For infinity set, some people can say that P of A should be there's no other set which larger than A, strictly larger than A, but strictly smaller than PA. So PA is the smallest subset which larger than A. So this is called the generalized continuum hypothesis. So you can go to Google or see other more advanced article to find whether you are interested in the set theory. I mean, this is fascinating results. Okay, so this is what I think this Cantor theorem is so amazing that the proof is amazing and the result is very enlightening. So you can think many like the philosophy or something. Okay, I will see you guys in the next set theory results, and I will see you guys in the next videos.